Hello, everyone. Glad to see you online. Welcome to the OC3 webinar. Today, we are glad to have our first speaker, Dr. Juan Muglia. First, I would like to briefly introduce Juan. Dr. Juan Muglia has a physics degree from the National University of La Plata, Argentina. Then he got his PhD degree from the College of Earth, Ocean, and Atmospheric Sciences, Oregon State University, under the supervision of Dr. Andreas Schmittner. His PhD thesis was on climate modeling of the ocean circulation and carbon during the last glacial maximum. He's currently working as a researcher at the Center for the Study of Marine Systems in Patagonia National Center, Argentina, studying the last deglaciation from a modeling and data analysis perspective. Juan is also the Pages data steward for OC3. The title of his talk today is the OC3 Deglacial Stable Isotope Database Features and Tools. If you have any question during Juan's talk, you can leave them in the chat box, or you can unmute yourself and directly ask towards the end of the talk. Okay, with that, let's welcome Dr. Muglia again. Juan, all yours.
Okay, thank you, Ning, for this nice introduction. Can you all hear me?
Yes, very clearly.
Okay, great. So I'm very happy that so many people showed up and is showing interest for this international initiative that is OC3. So as Ning said, the title of my talk is The Ocean Circulation and Carbon Cycling, Deglacial Stable Isotope Database, Features and Tools. That's a lot of words. Let's see what they mean. So the ocean circulation and carbon cycling, or OC3 from now on. OC3 is a Pages project, and one of its goals is the creation of a database of stable isotope data from benthic foraminifera, mainly delta C13 and delta O18, with a focus on the last deglaciation. So as Ning said, I work for CONICET here in Argentina, and then I'm also data steward. I have the support for Pages as data steward for OC3. So here I say that I am the author of this talk, but also all the OC3 members, and we'll first introduce some of them. So we have people from, as you can see in this map, we have people from all over the globe. We have people from the West Coast, like Dr. Schmittner, Mix, Isieki, people from the East Coast, like Dr. Elizabeth Sykes, from Europe, Lester Lemke and Jana Repschlager, who is the lead of the OC3 initiative, and then Stefan Mulitsa and Claire Welbrook. We have people from India, like Rajiv, well, me, myself. I'm down here in Argentina, and then we are gracious to have Ning currently on board organizing our series of talks, and many other collaborators all around the world who are providing data, who are helping us with quality control of the data that we already have, or calculating age models. And it's so many people that the map would be full of faces, and it would be very confusing to see. I just showed here the people that we monthly meet to talk about science and the OC3 project. And I want to thank Pages for all the support that we have had during these years. So we started this project, I don't know, Andreas Schmittner started it around 2013 or 14, and or maybe before that, and I jumped on board at around 2017. So the Pages Ocean Circulation and Carbon Cycling Working Group was established to gain a better understanding of changes in ocean circulation and carbon cycling, with a focus on the last deglaciation, so roughly between 20 or maybe 23 kiloyears before present and 15 or 14 kiloyears before present. The The project aims to study the ocean circulation and carbon of the last deglaciation from a global and dynamical perspective. To achieve this, a global database of delta C13 and delta O18 data from benthic foraminifera from seafloor sediment cores is compiled, and we call that the OC3 database. Since we are talking about the deglaciation was a very dynamic period of the climate history. So we care a lot about the time dimension and the evolution of those tracers through the deglaciation. So we also record for the, so we also store a chronology data and age models in our database. So we have from in our globe, in our world, we have sediment cores that come from the ocean. They benthic foraminifera are collected from them, and then we have papers that are mainly written or at least published on land, and using a computer down here in Argentina, we are putting everything together to form a database. So available data, there is a lot of available delta C13 or delta O18 data from sediment cores, but the methodologies from all those sources are not always compatible. So direct comparisons between different sites many times prove challenging. It's hard to compare a site in one place in the Atlantic with another site in another place in the Atlantic in the deglaciation, if they come from different publication and everything was calculated in different laboratories and the age models have different methodologies behind them. So tracer records from sediment cores need high resolution age models in order to capture the rapid changes occurring through the deglaciation period. So that is another challenge. The deglaciation was a much more dynamic climate period than, for example, the last glacial maximum or the late Holocene. So we need high resolution data. So we need data that has high time resolution. We want to be able to include data from different coring sites and their age models in the same deglacial analysis, because we want to include as many data as possible. We want to have our database to be as complete as possible and to cover as many regions of the world ocean as possible. So we have many questions like, can we transform a series of stable data, a stable isotope data and their age models into a 4-dimensional picture of the last deglaciation? So can we transform all this data that is around in different sources into what a modeler like I am originally would call a 4-dimensional matrix? So something that has information of position and depth and time. So to achieve our goal, which is to create a database that can be used in the way that I have been describing, we collect data from many sources. Some of it, I would say most of it is already published, but some of it is not, and they are original contributions of our members, of our contributors, and we carry out a manual quality check for each site. So we test, do a quality check for the original reference of the data, the number of shell measured to get each of the data points, the minimum and maximum mesh size used to collect the samples from the sediment cores, species-specific vital effects correction that were carried out maybe for the original publication of the data, and many countless other features concerning the data. Since we care about the deglaciation, and deglaciation was a very dynamic period, we only keep sites that have a resolution of 1 kilo-year or higher through the LGM and last deglaciation. And because of its epibenthic habitat and the fact that it's the species, there is a genus and species that better record or better trace the delta C13 of dissolved in organic carbon, we try to focus, so we try to use as many sites that have data from the genus, the Cibicidoides genus, especially the Cibicidoides were strophy species, as possible. So that's like, if you will, our favorite species and genus. However, some unpublished data of other species is also included in some sites. H models are standardized for our database, and we include all available H models for each site. For sites that have radiocarbon dates available, H models calculated with the Bacon software are preferred. The reason for this is that we want our H models to be as compatible with one another as possible among the different sites. So one of the so if they are calculated with the same software, with the same H model software, then that's much more likely that they are compatible. Our database is organized in different folders, each folder named after a specific coding site. The folders contain a number of files that store metadata, isotope data, and H models, and chronology data, I should say here. When an update is made, all the H models and or isotope data are kept in the database, allowing developers and users to easily compare versions, so we don't erase anything on our database, we just create new files. We include H models from original publications, in the cases when they can be quality checked, and also from some recent H model compilations, for example, Peterson and Lisiecki, 2019, Wallbreak and others, 2019, and Jonkers and others, 2020. I should also add to this Rapschlager and others from 2021. We also include, for many of the sites, state-of-the-art H models calculated specifically for this database. These are sites where that included that have radiocarbon data in their chronologies. So in those cases, our collaborators calculated H models using Bacon. In some cases, using the Incal 13 calibration curve, and then in some for some very recent calculations that Stefan Mulitsa made, we have H models using the Incal 20 calibration curve. So the database is organized in different folders. So this is a site and it has a folder, and then inside that folder we have depth in information. This what we call depth model. This is very important, for example, for IODP cores that have in a single site they take cores in different holes in a vicinity. Then isotope data, and we have as many isotope data as there are available. So we have different files. We have the H data, the chronology data that is used to calculate the H model, and then we have different H models. In something very important that we care about a lot is that in order to make the database compatible with all software and allow a broad spectrum of users, each file is files are organized as CSV or text files. So we have some text files where users or collaborators can write anything they want about the site and about the isotope data or chronology or H model or whatever characteristic of the site. And then we have CSV files like the ones here in this tutor. So here we have, for example, this site that is called ODP 138846. And here we have a CSVH data file and then several H model files. These numbers at the end of the H model files are just dates. in a in a format, in a year month format, year month day format, and then we have isotope data files, and and the fact that we use CSV files and text and TXT files means that any software can read these, or maybe you don't even need a software and you can just open them and look them with your eyes. This is especially useful because since we want this database to be useful both for data, for people who do data analysis, and for people who work with modeling, and for data people, I mean people who collect data, and then each of these scientists typically use different softwares. So by using the CSV files, like each of them can use their software, their preferred software, and any software can read CSV files. So for example, I'm very good at netcdf files, but if someone gives me a math file, then I'm fried. But in this case, a CSV file is okay with me too. And then maybe someone who likes MATLAB or likes R, but doesn't like netcdf or Python, then they can also read the CSV file. So anyone can read this, and it's very easy to edit. It's a very simple format, but at the same time, it's the only format that we know that that is reachable for everyone. So we have many folders like this one. I will go more into detail about that, about how many sites we have and all that by the end of the talk. But in order to, as you can see here, we have H model files and we have isotope data files, and this is kind of complex. It's in simple files, but it's still complex. So how do we handle this? So H model files typically have a different depth scale than isotope data files. For analysis, users require H models and isotope data in the same depth scale. So you want a matrix that is like, we have a column that is H and a column that is isotope data, and they are the same size, and we can plot them in an XY scatter plot. That's what we all want. So a Python script that we have written interpolates the H model scale to the isotope data depth scale. And no knowledge of Python is needed to use it, only to have Python installed in the with the packages NumPy, SciPy, and Pandas. That's something to install those packages is something that is one Google search away from anyone, at least anyone who has a Linux or Mac systems. I am not quite sure about Windows because I have never used Windows, but I know that it's that at least you don't have to operate with Python, because the script looks like this. For example, in Linux and probably in Mac too. So I write Python and then the name of the script. This is a preliminary name. Merge core files 4 version 4. And I type enter, and then we have a very simple interface which asks us what group of H models we want to use. For example, one is all sites with most recent H models. Then we also have 2 and 3 and 4, which are other options of other H model groups. We'll probably have, this is not in its most recent version, because we also have other H model groups now with like, for example, the INSCAL 20 H models calculated with Bacon that I mentioned a couple of slides earlier. So this is going to expand for the final version of the database. And then you type a number, and then all the job is done by this Python script without you seeing it. So you don't need any knowledge of Python. You need to have Python installed in these 3 packages. I acknowledge that. Not all Windows computers have it. All Linux systems have Python though. And then with that, you can get the interpolated H models to the isotope data depth scale, and then you're ready to do whatever you want because you have what you need: H model and H and isotope data together, one next to the other with the same size. So that now that we have H and isotope data files, we're ready to plot. Another Python script can plot time series of isotope data with the different H models. So I use, for example, the Python, and we are going to release these Python scripts to the public when we release to the public the database. This one, for example, here plotted the H model, the delta T13 against time of this site, GOB 9526. It's in the northeast Atlantic. And then here there are three different H models, one from Walbrook to 19, then this H model, which is either from Jonkers or from Repschlager, the 2020 and 2021 papers, or Pearson and Lisicki from 2018. So those are three groups of H models. And here I'm plotting the isotope data as a function of time for the three H models. And for example, one rapid thing that I can do here is compare how these H models, what the deglaciation looks for each of the different H models. You can see that we have an increase in delta C13 between something like 17 and 14 kiloyears before present. And well, there are lags between the different H models at when that increase occurs. So those are the things that we can do in the database. We can plot. We can also compare the H models and see how each of the features is captured and when these features are captured with each of the H models available. Another Python script lets the user plot different sites in the same figure. That script is under preparation, so I don't have plots to show about it. This Python script to create figures like this one is also going to be very user-friendly. You don't need to delve into Python to use it. You just need to type Python and the name of the script and just choose between different numbers, or probably choose between different names of sites. We can also calculate time slices for each site with another Python script. This one was written by Andreas Schmittner, my former PhD supervisor. Again, I write Python and the name of the script, and I just choose the name at the start year and the end year of the time slice. It tells me the number of cores that there exists with that number, and then in that time period, and then we get a time slice. So at different sites, the value that we have for that time slice in delta C13 or delta O18. And we can then plot things. This 48, this is a very low number because this figure that I captured here is with an older version of the database. What you can see, then you can use that to plot. For example, here I'm plotting three different time slices. Here I'm plotting, for example, the 23 and 19 kiloyears time slice for an Atlantic Ocean section of delta O18, and then the difference between that time slice and two other time slices, 19 and 17, and and this one is 17 and 15 kiloyears. It's the one in the middle is the difference between 19 and 17, and right is the difference between 17 and 15 and 19, 17 kiloyears. So this is the difference between two different time slices. And then this one is the LGM time slice, if you will. And for example, we can see here the decrease, we can see a decrease in delta O18 associated with salinity and temperature changes through the deglaciation in the Atlantic Ocean. And those are the things that we can achieve with this database. This is just a very preliminary show of what you can do and then the applications of it. Well, the same for the delta C13. Again, the same 3 time slices. So the LGM time slice on the left, and then in the middle, the difference between the LGM and the first deglaciation part. So between 19 and 17, and then the second deglaciation part and the first deglaciation part. So I divided it in 2,000-year intervals. So these time slices were calculated with this script, and then plotted with some favorite plotting tool. So to tell you about the current state of the database, we currently have 243 sites. 93% of the taxa is Civicidoides, and 76% is actually Civicidoides willerstorfi. We have 48 H models from Pearson and Lisiecki, 43 from Wellbrook, and 151 from either Jonkers or Repschlager H models. I put these together because they use, for most of the sites, they use the same methodology and share some of the H models. We also have 115 H models calculated for this database specifically. So new H models calculated with Bacon from radiocarbon dates, and some of them are INCAL 13, but most of them are INCAL 20. 70% of the sites have a resolution higher than 1 kilo-year between 23 and 14. So I'm in these 3 plots. I'm showing you in this first plot. What I'm showing you is just the sites that we have and their depths with a blue scale. And then here in the plot in the middle, I'm showing you the species. So the red dots are Civicidoides willerstorfi. The blue dots are other Civicidoides, and then the green dots are other species. And then on the bottom plot, what we have is the time result. So the number of data points between I think 23 kilo-years and 15 kilo-years. So some of the sites have very high resolution, 40 or 36 or 32 data points in that time interval. Then others have lower resolution. We try to keep only sites that have a resolution higher than 1 kilo-year, but we include in our database some previously unpublished sites that have a lower resolution than that. So that's why we have some sites that have a resolution lower than 1 kilo-year, but most of our sites have resolution higher than 1 kilo-year. Here I'm showing you a plot of the density, the number of sites in each 500 years time slice through in the LGM and deglaciation. And you can see that, well, for example, we have the highest number of sites that we have is in the deglaciation, maybe because of our focus is in deglaciation, and I look specifically, especially for sites that have deglaciation data. Now we want to be able to understand elastic glaciation from a global ocean perspective, but at the same time, we want to know how compatible different H models of different sites are, so we can know if we can use different H models from different sites in the same analysis of the elastic glaciation. we want to know if the stable isotope time series from different sites are comparable, and if the different H models available capture the same features of stable isotopes during the early deglaciation. So one of the first product that we will release with the database is going to be a comparison of the different time series, in this case delta C13, but also the delta O18, with each of the H models available. For example, see in this site here, we have two different H models, and the features and the timing of the features is very similar for all through the deglaciation, but sometimes we have higher lags. For example, here we have a minimum on the left panel. We have a minimum, and in this minimum there is a lag of about 1,000 years between two different H models. We can then, for example, make plots of, in this case, Atlantic zonal mean delta C13 with the different what we get with the different H models. Here I'm plotting just sites that are that have more than one H model available. So I'm comparing sites that are co-located in the different H model or in the different H model groups. For example, here I'm comparing the Jonkers and Rebschlager H model and the Wellbrook H model. So here I'm plotting the delta C13 using for three time slices, the 23 and 19, 19 and 17, and 17 and 15 kilo years. I'm plotting these three time slices of Atlantic zonal mean data. In this plot, it's interpolated data. And what you can see is that for each time slice, you get a very similar figure using the both here on the top line of plots, you have using the Jonkers or Rebschlager H models, and then on the second from the top, you have using the Wellbrook H models, and you can see that the features that are captured in the delta C13 Atlantic zonal means are very similar. So that's a simple H model analysis that you can make using our database, and it's going to be released. This analysis is going to be released in the paper that we plan to submit when we may publish the database. So what I lastly want to say is that we need you, if you have published data that was never published, or we have data that you know a lot of and you can help us with the quality control, and or if you are an H model expert and you want to calculate H models, then you can sign in as a collaborator for OC3, and then when you very soon we plan to submit this first version of the database in the first half of this year. So in the first half of 2022, we want to submit the database to for example, to Pangea or to NOAA data collections. And we will also publish or submit a data focused paper, probably including the H model comparisons. And if you collaborate with us, your name will be in that database and your name will be as an author of that paper. Another important aspect of OC3 is that this job is not finished when we finally publish this paper and when we publish this database. We are going to let users to continue collaborating with us and continue to expand the database with new data or new H models or new interpretation of the same data or new chronologies. So the database will be flexible enough to include new collaborations after it's published, so there is no rush. Even if you are not ready to share data with us or to calculate H models with us for this goal of submitting the publication at the first half of this year, you still can collaborate, and we will be around as a group, hopefully for many more years. Thank you.
Okay, thank you, Juan. Very informative talk. Are there any questions for Juan? Maybe I can ask a question first. So Juan, for the H models that you mentioned, so for the new H models that you mentioned, when you calibrated radiocarbon dates, how did you deal with the, the reservoir ages?
I didn't calculate most of the H models. The H models were calculated by our collaborators, but yes, we have the information about the reservoir ages. Off the top of my head, I don't remember, but we take into account the reservoir ages.
Yeah, because on one of your slides you mentioned there are like 151 records either by Lucas Yonkers or Jana.
Yes.
So I know the work by Jana because
yeah. Right. Those H models were those H models were taken from those publications and included in this database. We also have new H or original H models that from different sources of different collaborators calculate different H models. We have set the standard of using Bacon and first using INTCAL 13 as the calibration curve, and now we are using INTCAL 20 as the calibration curve. We also have standards for the reservoir ages, but at this moment I don't have the information available here.
Okay, so but are those, are those records treated with the same standard for the radiocarbon age? For example, you can either use the radiocarbon ages that was reported from the original publication, or you can use the simulated reservoir age by boosting maybe 2020. Yeah, so it's what are the standards the same?
I think that for the at least for the 2013 sorry, for the INTCAL 13 H models, Butsin was used, but I don't want to say that it was used for all the H models because I am not sure. But at least for the INTCAL 13 H models, it was.
No, I think in the Butsin H model came out later than the INTCAL 13, right? Probably the earliest version was 2017.
No.
So maybe.
But the H models that I'm mentioning were calculated between 2019 and 2020. The ones that that use INTCAL 13.
Oh, that's true. Yeah. The INTCAL 20 was arrived later. Okay. Yeah. I just think it's important to to really make sure that all the standards are the same.
I don't want to. Yes, but I don't want to say, and the methodology for the reservoir age is this one, because off the top of my head I don't remember. It's different for different latitudes, and I have the information, but I don't have it here right now.
Yeah, sure, I agree with that. Yeah, especially for high latitudes, I think the simulated reservoir age by Butsin is probably, I wouldn't fully agree with that results. Yeah. But Yeah, but for low latitudes, I
Yes,
think
for high latitude,
it's a good.
we use a different reservoir age methodology for high latitudes than low latitudes. That's for sure. Hi, Julia.
Hello, everyone. Hi, Ron. Hi, Ning. Thanks for this talk and thanks for setting this whole series up. I have a question. So I congratulate you that you want to publish the database sort of within the next 4 months or so. Are there plans that after the publication of the database or the sort of official launch of the database, that people can submit data so that it can continue to grow? Is there some function set up for this?
Yes, yes. Uh, I will have funding from Pages for as a data steward for a while. So in the beginning, and then maybe the function will be just to sending me the data, but then one of our goals is to set some more automatic way of submitting data. But still, since we want to have quality control, there is always going to be a human between the new data or the new age models and the database, because we don't want it to be just a place where people dump data. We want some expert insight on the data and on the age models before they go and are included in the database.
Awesome, thank you.
Juan, can you see the 2 questions in the chat box?
Yes.
Okay.
Yes, here. Bianca Sony, maybe you have explained it already and I missed it. Are you any consider benthic forams for age models? If yes, then why not planktic forams or offset? Well, we have most of the radiocarbon data of that in the chronologies is from planktics, and we also have these other sources of data for chronology, like for example ash layers. So I don't think we have any. Well, we have some age models that use O18 alignment. If that's what you mean for as for benthic forams as age models, then the answer is yes, because we have some sites that use O18 alignment for the age models, so what they call wiggle matching. If the age model we have different methodologies in our age models. We also have some sites that have what is called the plateau C14 plateau tuning for the age model. Since we include all the age models available for each site, as long as they are quality control, we can include other methodologies for age models. I just mentioned the radiocarbon-based age models because that's what most of the sites have, but we definitely have age models that use other methodologies and want to include those age models, and it's going to be and that's going to be very interesting because since one of my goals at least is to compare how the evolution of delta C13 and delta O18 with the different age models, then if we have other methodologies like the ones you mentioned, it makes for a much more rich discussion on the age models. Are you, Peter Kohler, are you planning only OC3 data in the upcoming paper, or are you also planning to include first model-based interpretation? No, we want to release the database in the paper and the age model comparison, and then for model data model comparisons, we have another paper which will use this data for the validation of model simulation, similarly to what we did with Andreas Schmittner in our 2018 and 2021 paper. but in this case, more team work because it's a deglaciation, and we will have time. So that's one of our variables. Right. Wellbrook is an example of a model of an edge model synthesis that used wiggle matching. So so yes, we include if you have sites where you do a delta 18 alignment, then yes, we will definitely like to have those sites and include those edge models. Okay, anyone else?
Can I ask one more question?
Yeah, I think, yeah, Julia, please.
Sure, yeah.
Juan, can you elaborate on your motivation to compare the different age models? Because there's so many different nuances on how they are established. You know, one uses Bacon and the other one uses undateable, or you know, or some use SST alignment to sort of polar ice cores and use the reservoir age sort of constraints. So I wonder how informative, like a sort of detailed age model comparison will be.
I'm interested in compare. So since I'm a modeler, the ultimate goal, one of the ultimate goals of this project, at least in what concerns to me, is to be able to compare the models with data through the deglaciation. Now, different sites have different. Some of the sites, there are different sites, and they also have different age models. So the age models come from different sources, as you mentioned. Well, I really want to know. I'm very interested in seeing if you can use at the same time site A that has one age model with site B that has a different age model methodology. How close are the features that are the jumps associated with the last deglaciation captured by these different age models? So one way that we can at least have a hint of how comparable these different age models are is to compare how they behave for a single site where more than one of these age models is available.
But we know, I mean, if we go through the papers, Walbrook, the Lisicki paper, the Repschläger paper, we should make an inventory of how the approaches are, what the approaches are. And based on that, we can already sort of estimate what potential age model offsets will be, you know? So it's sort of a sort of top-down approach. You are doing the bottom-up approach, which is probably more time-consuming, you know? So I could imagine that at the end, you sort of come up with the idea, okay, age models do not matter much, or age models, the age model uncertainties are sort of are on the order of 2 kiloyears or something for the LGM, or even more, obviously, or likely. So I wonder what the potential outcome of such an exercise will be, you know, because in the end, you will not know what age model is the correct one.
Right, yes.
It's the more robust, not robust one, but the sort of more representative of the actual actual climate in the past.
One thing that we're seeing, for example, is that the difference in the timing between the different age models is usually smaller than the uncertainty of the age models. That's
Can you say that again? The what?
The difference in the timing of the so the lags between the age models are, we are seeing that they're typically smaller than the uncertainty of those age models.
Yeah, yeah.
Of each of the individual age models. So that's, for example, something that tells us that maybe it doesn't matter that much which H model that you use, because the differences are inside the uncertainty bands. So that's something that we learned doing the analysis that we're discussing. It's possible that we would have been able to learn somehow something with a different approach, but in our approach we found this.
Yeah, I agree with you that H models are probably larger than usually reported. Would it be an option? Sorry.
Yes, Andreas Schmidtner also is mentioning, Julia, it is an attempt to quantify uncertainty associated with H models. So
yeah, I mean, H models is on one side of the medal and H model uncertainties is the other side of the medal, and it's critical for this project. I agree. Would it be an option? Sorry, I'm taking this Q&A session. Would it be an option to decide for one H model approach and then use it for all cores in the database, with the disclaimer that it's probably very difficult to decide what that particular H model approach would be?
Well, for users, it's possible, because as you saw in the interpolation scheme, you can choose what H model group to use to plot the data, for example, or to get the interpolated isotope data. Sorry, the interpolated H model to the isotope data. Now, for us, if we include only one H model methodology, then, well, first, one of the original goals of this database is to include all H models available for each site, and let users to decide which H model to use. And also, our number of sites would be diminished, because some sites have radiocarbon, or some other sites use separate layers, and so on. And then the number of sites that would be available for a database will be much less. We already have a very important constraint in the fact that we only try to include sites that have a resolution higher than 1 kilo-year. So that's why we only have 240 sites and not, I don't know, 1,000. So if we also include another restriction, which is only use H models of such and such characteristic, then it's going to be, I think the number of sites that we will have is going to be much less. Still, users can use that such a restriction, because each of the H models is tagged with a different kind of word in their names, so they can choose what H models to use. So we let that for users too.
Yeah, I stopped. That's fine. Thank you.
Okay, are there any other questions? Okay. Yeah. If not, then let's thank Juan again. Also, I want to, ask people who attend the talk today, if you or someone else want to give a talk related with ocean circulation or carbon cycling, then you please let me or Jana know, then we can arrange your talks in the future. Okay. Thank you very much. I think with this, maybe we will end the talk today, and we look forward to seeing you in future talks.